So today we continue with Bayesian model selection and parameter estimation. And so, well, what we already saw yesterday is that if you want to do parameter estimation, you can compute the posterior density function by taking the likelihood and multiplying with the posterior. And then, well, usually there are many different parameters in the problem, but if you're interested in only one of them, so you want the posterior density function for instance, mass 1, then you just integrate out all of the others. Then on the other hand, you can do model selection. And there what we do is compute an odds ratio, which is the evidence for a hypothesis H1 divided by the evidence for hypothesis, or actually the posterior probability, I should say, for H1 divided by posterior probability of H2, which is equal to a ratio of evidences times a ratio of prior probabilities. And then to obtain the evidences, you just take the likelihood function and you integrate it against the prior, and there we are. And then a practical way of doing this in these high-dimensional parameter spaces is, for instance, nested sampling, where the evidence is obtained by this iteration process involving shrinking prior mass. And then in one go, you also get posterior samples for your posterior density. And of course, these equalities should not be taken as literal equalities, but you will get extremely good estimates, and you can actually pretty well quantify what the errors are that you're going to make. So this is what we did yesterday. So for quasi-circular inspiral, as I keep saying, there's a 15-dimensional parameter space. Here are all the parameters. But also we have different detectors, D, which have different responses to signals, and we have to take that into account. And that's actually very simple because the different response comes in, well, okay, the different response comes in two ways. One is the different orientations that the detectors have with respect to each other, and the other is the differences in arrival time of the gravitational wave. So in particular, this delta TD is the difference between the arrival time at detector D and the arrival time at the center of the Earth. Then also different detectors will have different noise realizations and therefore different noise power spectral densities. And so this can be folded in fairly easily. Well, yeah, so examples of, again, of generative hypotheses. One hypothesis could be that the data is pure noise, so there is no signal in the data after all, or the signal the data contains a signal from a particular family, like post-Newtonian inspiral waveforms or inspiral merger ring-down waveforms that have been tuned to numerical relativity results and so on. So, well, the probability for the noise realization in detector D is given by this Gaussian here in terms of this inner product, this noise-weighted inner product. And then that gives us the likelihood for the hypothesis N. Well, in this case, actually, no parameters are involved, so I should have left out the vector theta, and this is simply what you get. Then similarly, the likelihood for the hypothesis where there is a signal, again, of a certain family, is this here for the Dth detector. We will have data from all, from all sorts of detectors, LIGO Hanford, LIGO Livingston, Virgo, LIGO India, Kagra. And so to get the joint likelihood, it's very easy. You just multiply likelihoods and you're done. And so from this joint total likelihood, you could compute everything else. You can do parameter estimation and model selection. So, and this I already showed yesterday. Let me just skip this. Okay, so you have these posterior densities for parameters. Now, what I didn't say yesterday is that you get a posterior density. Of course, you get it in the sense of posterior samples, and that is still have to smoothen or interpolate to get some smooth function that you can then use to marginalize to get a posterior density for one parameter in particular. So there's some minor technology involved in going from here to individual posterior densities. Or you can get the posterior density for two parameters jointly and so on. Then often it is useful to change to different sets of parameters. For instance, you might want to know the density distributions for the component masses, or you might want to instead look at density distributions for chirp mass and the mass ratio. And in making that change, it is not like you have to do the nested sampling all over again. You just do a coordinate transformation, and so the posterior density distributions in terms of one set of parameters compared to the other just involves the determinant of the Jacobian, and you're done. Okay, and here are some examples. This is a binary neutron star coalescence with these component masses, a distance of just over 150 megaparsecs, in simulated Gaussian noise for advanced LIGO and Virgo at design sensitivity. This is what you get for M1 and M2. The red dashed line indicates the true value of the parameters, and this is included indeed in the posterior density distribution, although you see that there is a non-negligible spread. You can also look at this in terms of the chirp mass and mass ratio. And then you see a very different picture. So here is chirp mass. So the way you should read this x-axis, like it says, you should add 1.1245. But you immediately see that chirp mass is incredibly well determined, right? So like Cole said, it is at the sub% level, even for sources that don't have an SNR very much above threshold. And then here is the posterior density distribution for the mass ratio, which is quite spread out. And then, of course, you can look at joint posterior density distributions, for instance, for M1 and M2. Here they are. The dot indicates the true value, and you see that you get a 2D posterior distribution that is quite smeared out. In fact, it looks like it is smeared out along a curve. Can anyone tell me what that curve could be? Yes, it is a curve of constant chirp mass because, of course, that is extremely well determined. And then what is of interest to electromagnetic astronomers is to know the position in the sky, so that they want to know it fairly quickly. So we're not going to run the full nested sampling toolbox. We'll do something. Sky position determination can be done more simply and almost as accurately as with nested sampling. Namely, you can look at, first of all, times of arrival of a signal in the 3 different detectors, which is also very well determined, in fact. Then you can also fold in the different orientations and the different phases at arrival at different detectors and triangulate. Yes? Yeah, so it is because yesterday, in yesterday's tutorial, you saw a waveform at 0 pn, both in amplitude and in phase, right? And so the way masses enter into the amplitude at that pn level is simply through the chirp mass to some power. And so that is the basic reason. And then the mass ratio also appears in the waveform if you switch on the higher pn orders, but those, of course, are suppressed by powers of E by C.
But there are quantities like TC as well, right, which also appears in the waveform,
yeah.
time of coalescence. So, by an extension, should TC be also well measured?
TC is extremely well measured, yes. Yeah. In fact, I think 2 lectures ago, I talked about this blind hardware injection that people did, right? Well, there was a clever guy in the collaboration who immediately said, I know that this is a blind hardware injection. I know that this is not a signal. Okay, how do you know that? Well, the idiots injected on an integer number of seconds, GPS seconds. Okay. Okay. So then, so this is parameter estimation for a single source, but we'll want to, in getting all sorts of scientific results, you'll typically want to combine information from multiple sources. Now, a problem is then that masses, sky position, distance, and so forth are incidental, by which I mean that, each time we find a signal, nature will have thrown a different set of masses and distances and so on at us. But of course, it will be of great interest to see, for instance, how binary black hole masses are distributed, because maybe that can give some insight into the formation mechanisms of black hole binaries. But generally, we will often want to check some functional dependence or other, for instance, the dependence of post-Newtonian parameters on masses and spins that can be used to test general relativity, or the neutron star equation of state, which is a functional dependence of pressure in terms of density, or equivalently neutron star deformability as a function of mass. And so there are two ways of doing this. Well, unsurprisingly, I keep talking about these two ways of doing anything. Hypothesis testing, compare different functional dependences in this case, or measure parameters that determine the functional dependence. In other words, if there is some functional dependence like P of rho that you want to measure, then maybe you want to model P of rho with a finite number of parameters, and then those parameters will be the same for all sources because they are the parameters that determine the functional dependence. And then there will be a way of combining information across sources to get a much sharper result. So yes, assuming that the functional dependence is universal, as we can reasonably do, as Cole explained, in the case of neutron star equation of state, and certainly for the dependence of post-Newtonian parameters on masses, then we should be able to combine information from multiple sources. Okay, so the first example, that will be the rest of this lecture, will be constraining the equation of state of neutron stars, and then tomorrow's lecture will be about testing general relativity. So, as binary neutron stars spiral towards each other, they're going to start feeling each other's tidal effects. Now, the tidal tensor of one star to leading order will induce a quadrupole deformation in the other star. Now, there's a relationship between those two, of course, in terms of this prefactor here, which is called, sensibly enough, the tidal deformability, and this depends on the neutron star equation of state. That is how we're going to extract information about P of rho, or M as a function of R, from coalescence observations. And so, well, the way this deformation enters the waveform is that neutron star deformations will affect the surrounding space-time curvature. This in turn has an effect on the orbital motion, in particular the angular motion, which we can measure very easily because essentially the gravitational wave phase is just twice that angular motion. Now, a problem is, or a potential problem would have been, that contributions to the phase due to these tidal effects don't show up until very high effective post-Newtonian order, namely 5 p.m. order in the phase. However, the saving grace is that the prefactor is going to be rather large. So the way this lambda of m actually enters is always in the combination lambda of m divided by total mass to the fifth. Now, lambda of m is roughly proportional to the radius of a neutron star. So this goes like radius of individual neutron star divided by total mass of the system to the fifth. And then this is going to be in the range between 100 and 10 to the 5. So despite the fact that these tidal effects appear at very high post-Newtonian order and will be suppressed by a high power of V by C, the prefactor is large, and that is why we can hope to learn something. Sorry?
There's no factor.
I know. I'm talking about effective post-Newtonian order, as I said. I know, yes, it is. But you know, for observational purposes, what is important is, well, you know, at what p.m. order can you collect it, right? And that is what matters. So the question is then still, you know, this is pretty high order. Can we constrain neutron star equations of state with gravitational wave observations? That is still not obvious, and we need to check with simulations. Well, first of all, this is a plot that I think I showed earlier. Like Cole also explained, I think the equation of state, P of rho, maps to a relation between mass and radius. And here you have a whole bunch of predictions for the neutron star equation of state with different underlying assumptions. And you see that there are some observational constraints from mass measurements of neutron stars. But nevertheless, a large number of equations of state, and there are of course many more that are not shown in this plot, are actually consistent with existing measurements. And so there is an interesting problem to be solved here for sure. But again, can we solve it? So first of all, equation of state P of rho, like I said, maps to this tidal deformability lambda of n. And so here are some examples with different underlying assumptions. So H is hyperons and pi is pions. Here you have strange quark matter. I guess these are more, I don't know, standard models in some sense. But in any case, in each case, you have a range of predictions again for lambda as a function of n. Okay, so now in trying to find out which of many possible equations of state is the right one, first we look at hypothesis ranking. Then we'll see, we'll also be able to do something with parameter estimation. Okay, so how does that work? You take a set of necessarily finitely many equation of state models, and to this correspond a set of hypotheses such that Hi is the hypothesis that Mi is the correct equation of state. Now, each equation of state model comes with a particular dependence of lambda on m, so a particular functional dependence. Now, let's say that H with label I is the waveform model whose EOS contributions are determined by that particular functional dependence. Then you can trivially write down the likelihood function for each hypothesis Hi, and it is just given in usual form. And the particular waveform family you choose here is the one that has this functional dependence lambda of n. And so, and then you can go on and of course compute the evidence for Hi, and that will be the basis for comparing hypotheses. Okay, so as usual then we compute an odds ratio, which is a ratio of prior probabilities and a ratio of evidences. Now, like I said, an important bonus will be if we are able to combine information from multiple sources so as to get a stronger result. And so is this possible? Well, here is that same odds ratio, but now assuming that n detections have been made of binary neutron stars. So, well, as usual, it's a ratio of posterior probabilities. And of course, using Bayes' theorem, this can be written as ratio of priors and ratio of a combined likelihood for all of, or a combined evidence rather, for all of those detections together. Now, one of those likelihoods is just a probability for D1 having been observed, and D2, and D3, and D4, and so on. So in terms of a probability, and also assuming that different detections are independent, this is just a product of probabilities, right? And so the individual probabilities in the product are just the likelihoods for the individual detections. So we're easily done here. The odds ratio for a whole set of detections is just, again, the ratio of prior probabilities, and then simply the product of the odds ratios for the individual detections, and that's it. So hypothesis testing then trivially lends itself to combining information from multiple sources, and this is in fact what you need to do. So let's now go to an example. We're going to consider, for simplicity, just 3 equation of state models for both the simulated signal and the hypotheses. One, well, it's a pity you can't see the middle one. It is light green, or at least I can't see it. But or yellow. I'm also colorblind, in fact. It's true. But in any case, what we picked here was a very stiff equation of state, and it's called MS1 for whatever reason. And then there is a moderate equation of state, and then a soft equation of state. And also, in addition, we'll consider the so-called point particle hypothesis, which says that, well, literally the neutron stars are not neutron stars, but point particles. They have no extension, and that's the same as saying that the tidal deformability is 0. So the idea is then to check if we can at least make a difference between a hard, a moderate, and a soft equation of state. If we can't even do that, then it's hopeless to do something more detailed.
Assuming that whatever we see these DN measurements, we are seeing neutron stars which are all, they are standard in some sense. I mean, we are assuming that they will have one particular equation of state.
Yes, so yes.
For example, he mentioned that there could be many things that could be happening inside neutron stars. We don't know.
Yeah.
It's made of quark matter, this matter, that.
Yes.
So, but we are assuming here that there is some standard
Yes.
neutron star with some equation of state. We don't know how it, I mean,
Yeah.
The MIs are how P depend on rho, but there will be only one kind of P dependence.
Yes, exactly. Yes, that is the
And
assumption.
all these DMs that we see, they all are some standard neutron.
Exactly. Yeah. But we will make different choices for the simulated signals that we put in the data, right? So, but in each case, the whole set of detections will have the same equation of state. That's true. Yeah. Okay. So, so these are the three equations of state we will be considering, plus then that point particle idea. And so, what am I showing here? Okay. So first of all, you can simulate a large number of catalogs of 30, for instance, 30 binary neutron star detections each. So what I mean is the following. So we put an enormous number of simulated signals into the data, and we we do our data analysis magic, and then we randomly bunch the results in sets of 30. The idea being that maybe nature, during the duration of the advanced detector project, maybe nature will only ever give us 30 detections, okay? But we do want to know how results depend on what the individual component masses will be of those in those 30 detections, what the distances will be, and so on, and also the effect of different noise realizations in the detector. So, but the idea is that 30 detections is what we will have to work with, and we combine evidences from those. Now, again, you can't see things very clearly because of these pale colors, but let me first explain what you're seeing here. So, for instance, in the top left panel, what was done was we injected the point particle equation of state, quote unquote, and then we computed the following base factors, so, or rather odds ratios. So we computed the odds ratio for MS1 versus the point particle, the odds ratio for this H4, which is the intermediate equation of state against the point particle, and the odds ratio for SQM3, which is the soft equation of state against the point particle. So now remember, we have many different, so for each of those three, we will have many different odds ratios, and each pertain to 30 detections, of which we've combined information. And then you can look at how these odds ratios are distributed, and in particular, what I'm plotting here is the cumulative distribution, okay? So what does that mean, cumulative distribution? Well, for instance, in this, is this green or yellow? I can't tell, but green, okay. So that is the middle dotted line here. So in 50% of the cases, in 50% of the cases, this number here will be smaller than -50. Okay, so, and by the way, what I'm plotting is not cumulative distribution of the odds ratios themselves, but of the log of the odds ratios. Because it turns out that odds ratios often are either very small numbers or very large numbers, and not very human-sized therefore, but the logs are. Now, we know, because we put in the signals ourselves, we know that the equation of state in the signal is in accordance with the point particle model. So therefore, in an ideal world, it would always be the case that the log odds ratio for MS1 versus point particle is smaller than 0, because the odds ratio itself for MS1 versus point particle is smaller than 1, right? Because MS1 is not correct. PP instead is correct. And similarly for H4 versus PP, and for SQM3 versus PP. Okay. So again, what I'm plotting is cumulative distributions for these three odds ratios. And what do we see? Well, let's focus first on log odds ratio for MS1 versus PP. You see that in almost all of the cases, in almost all of the catalogs, indeed, MS1 is deprecated because the log odds ratio for MS1 versus PP is negative, correctly so. But not in all of the cases, and the remainder here is due to detector noise, having made it very difficult in almost all of the detections to, for the algorithm to find what the correct equation of state is. And this will happen. We need to live with this. Then, we know that MS1 is the most different from the point-particle model, right? Because MS1 is the hardest equation of state and therefore can support the largest radii. That's the most you can get away from the point-particle idea. And indeed, out of these three here, you see that it is the most deprecated. The least deprecated should be the equation of state that is the softest and that therefore corresponds to the smallest radii. And that is indeed the case. Here is the distribution for SQM3. And then, as expected, the moderate equation of state lands somewhere in the middle. Okay? So all this makes sense. Then you can go the other extreme. You can insert simulated signals into the data that are MS1 injections. And so MS1 is our hardest equation of state. And so what I plot in the top right panel is instead log odds ratio for first PP versus MS1, and then log odds ratio for H4 versus MS1, and log odds ratio for SQM3 versus MS1. So since we already know, well, we put in the signals ourselves, we know that MS1 is correct. So if there were no noise effects, then in all three cases, it should always be the case that these log odds ratios are negative, because PP is not the right model, and H4 isn't, and SQM3 isn't either. So what do we see? Well, this time, what is most deprecated, that is most negative log odds ratios, is the PP versus MS1. Entirely as expected, because now what the signals have is this very hard equation of state, large radii, that is the furthest away you can get from the point-particle model, and indeed the point-particle model is the most deprecated. What is the least deprecated is this intermediate equation of state now, because the intermediate equation of state does allow for large-ish radii and is therefore closer to the true equation of state, which allows for the largest radii. And then in between this time is this soft equation of state, SQM3. So all is as expected, and this formalism works. Except that, of course, you should, this should not come as a surprise. You should expect that, you might be extremely unlucky and the noise might push all of the, in all of the cases, for almost all of your detections, the noise might push you away from the truth. And then, well, you can play the same game by injecting, as we call it, the intermediate equation of state and the soft equation of state, and this correct ordering generally holds.
So
yeah.
The numbers you have here kind of bug me a little bit. If you look at the bottom right diagram, so we've got an SQM3 injection, and you're looking at the point particle of these other things. Since it looks like there's a 10 or so % chance of having a log odds ratio of plus 25
Yeah.
or greater.
Yeah.
And what I thought I understood in terms of what an odds ratio means between two particular models
Yeah.
is that if those are the only two models of the universe, that odds ratio, not log odds ratio, that if you have an odds ratio of like 100, you're expecting roughly only 1 in 100 chances with the deprecated model in fact be the right one. So e to the 25 is a lot bigger than 100.
Yeah, absolutely.
So it's absolutely enormous. And so I don't understand how it is that you can have such a large fraction of these cases giving such a huge odds ratio.
Yeah.
Could you explain that a little more?
Yeah, so the reason is, I'll explain it qualitatively, not quantitatively, but the reason is that on the one hand, your signal amplitudes are very much smaller than the typical amplitude of the noise by a few orders of magnitude, in fact. So that already makes the detection problem difficult, as we know. But also, this is intrinsically a very difficult measurement, because the effect you're interested in, again, appears at very high post-Newtonian order. And despite the largish prefactors that we expect, that's going to cause difficulties. And indeed, people are often surprised about these very large odds ratios, never mind log odds ratios that we see. But this is what we have to live with. Okay. So, constraining equation of state, with hypothesis ranking, I wanted to make some notes, I guess. Yes. So we've only considered 3 models. Now, however many models you use in your ranking, in reality, the true equation of state is probably not going to be among them, right? Because that would be an extraordinary stroke of good luck. However, you could expect the top-ranked equation of state model to be, in some sense, close to the true equation of state. And I'll let you figure out what close might mean in this context, but this is a general expectation. Now, even if the true equation of state is in a list of hypotheses, it will not necessarily get ranked the highest. Noise effects can interfere with the measurement, and like I said, the measurement is intrinsically difficult, and we've seen how badly wrong it can go. However, the internal ranking of hypotheses that we've seen is largely as expected. So for instance, if the equation of state in the signal is a stiff one, then a point particle model will be most deprecated, and the next most deprecated will be a moderate EOS and then a soft EOS. So generally things work, but expect possible mishaps due to the difficulty of the measurement. Okay, so that was constraining equation of state, or at least getting information about the equation of state by computing evidences and then odds ratios and then ranking hypotheses. However, we can also do something with parameter estimation. You can of course measure or try to measure lambda of M1 and lambda of M2 separately for each source, but that will turn, well, then you get individual lambda measurements, which then in principle you could compare with the individual component mass measurements and then somehow construct the corresponding lambda of M, which will have some error bars or something like that. Well, that turns out to be a lousy idea. A better idea, and also more elegant, is to identify parameters to characterize this function lambda of M. And now, you might say, well, then in principle you should allow for infinitely many parameters characterizing this function, and you can't do that. Indeed, you can't, but the expectation is that in any case, again, because of the difficulty of the measurement, only a finite number of parameters are going to be measurable at all. So that is fine. And then you have to choose those judiciously, of course. But if you identify a number of parameters that could characterize lambda of M, then they will be the same for each source under the assumption that, again, that the equation of state is the same for each neutron star. And then it should again be possible to combine information on these parameters using all the available detections, because the numbers you're measuring are the same for each and every source. Now, so that means we need to parameterize this function lambda of M, and there are different choices that people make. One is to actually look at the underlying P of rho from which lambda of M can be obtained, and then model P of rho by so-called piecewise polytropes. So in particular density intervals, P of rho will take on this form, some power law, but in different intervals you'll get a different P factor and a different power of rho. And this then has a certain amount of theoretical justification. And then on the other hand, you might say, well, I'm an observer, the theorists can figure it out later. What I'm going to do is simply write my lambda of M as a Taylor expansion around some reference mass. So M naught could be, I don't know, 1.4 solar masses. I can be fairly certain that the range of masses that are possible for neutron stars will not get very far away from those, and that is what I'll do. That is a perfectly fine choice. Yeah.
So if you don't, so you said that, the top rank, equation of state cannot be close to true one.
No, the top rank probably will be close to the true one. Yeah, of course. Then, yeah.
Which one you will prefer? If you are not sure.
The answer is you don't even know. You won't even know, because unlike God, we won't have access to the signals directly. We can only measure and compare. So this is an intrinsic hazard of this job. You won't know.
Yeah, but our whole aim is to compare hypotheses.
Yeah.
Sure,
and then hope that you can trust your result in some way, right? Or to some extent. We've seen to what extent you can trust the result in the case of second generation detectors, we can do better than this. We can, by building Einstein telescope. That is what we'll do, hopefully. So, but yes, this is a limitation. I mean, this is, you know, this is always what happens at the frontier of physics. Things will not be so easily measurable and so easy to disentangle at the beginning, and later on, it'll get better. So, but returning to parameter estimation, so like I said, you want to identify parameters that characterize this function lambda of m. And so in the case of the piecewise polytropes, those parameters would of course be those prefactors and those powers of rho. Or in the case of a Taylor expansion, it is simply the coefficients in this Taylor expansion. And those you assume to be the same across sources. Now, the choice I'll make here is to go with the Taylor expansion. As it turns out, it doesn't make much of a difference. The same or the same results that I'm about to show have also been worked out in the case of the piecewise polytropes, and qualitatively the results you get are pretty much the same. Now, we can't take this Taylor expansion to infinite order, of course. We have to cut it off somewhere, but like I said, the general expectation should be that only a finite number of coefficients can be measured anyway. And so even if you cut off this Taylor expansion at some finite power of m minus m naught, then you can still, to good approximation, assume that this finite number of coefficients will be more or less the same for all sources. Okay. So now we need to construct a waveform model again, of course, and the waveform model will now have this dependence on parameters. So the theta vector here is all the parameters you would have in any case in the point particle model. And the C parameters are simply the coefficients in this truncated Taylor expansion. Okay? So what we had previously in the case of model selection, we didn't have any extra parameters, only the point particle parameters, because for a given equation of state, you know, you have a given lambda of m that you put in the waveform. So there are no extra parameters. Here there are, however. Okay. What is then the likelihood function for a single source? Well, it is of the usual form, of course, and I put my waveform model here. All right. So this is the likelihood for a single source. Then you can compute a joint posterior density distribution for all of the parameters, so the point particle parameters as well as the new ones. And then if you're only interested, for instance, in the 0th order coefficient in this Taylor expansion, you marginalize over not only the point particle parameters, but also C1 through Cj max. But again, the question is, how do we combine information from multiple sources? Okay, let's give it a try. So again, let's focus on the posterior density function. We're doing parameter estimation now, but let's focus on the posterior density function for one of the parameters, and I could have chosen C1 or C2 or C3 here, but let me just choose C0. Then, well, like I said, that is just the joint posterior density function, but marginalized over the parameters I'm currently not interested in. Now, given multiple detections, what I actually have is a posterior density function, C0, given all these detections in the bin. I can use Bayes' theorem, of course, so then I get a combined likelihood for all of these detections times the prior on C0 divided by probability to get all, divided by essentially an evidence. Now, P C0, so the prior on C0 I'm going to throw in front here, but again assuming independent detections, we can write these probabilities here just as product of probabilities. So nothing special going on here, that is the same as before. Then on these individual likelihoods, I can again apply Bayes' theorem and write these in terms of individual posterior density functions given individual detections. And then you see this unwanted factor here, P, probability of the data drops out conveniently, and this is what we have. Now, in the denominator, because of our usage of Bayes' theorem, you now have the prior on C naught again, but you have it n times. So if I throw this outside, we have the prior on C naught to the power 1 minus n, and then simply a product of posterior density functions. And this is again fairly intuitive, right? So you have, so the first source gives you a particular, so this is C naught. The first source gives you a particular posterior density function. And then the next source will give you some other posterior density function because the noise realization will be different. And then there will, of course, be a third one, and so on. And to home in on the correct or the best value for C naught, what you do is you just multiply together all of those posterior density functions, and that is it. You only have to take care that you multiply by this factor in terms of the prior, and you're done. And of course, as you keep multiplying posterior density functions like this, you can imagine that the result will get more and more peaked, right? I think everybody will see that. Okay, now interestingly, this can actually be viewed as follows. The posterior of the nth measurement becomes the prior for the n plus 1th measurement. I'm going to leave that as an exercise. Okay. So what is that going to mean what will that mean in practice? So this is what I just said. This is how we're going to compute posterior density functions using all the detections we will have. And recall that we did this Taylor expansion of lambda of m. And for definiteness, and also since these are costly simulations, we don't want to take up too many computational resources, we're going to restrict this Taylor expansion to quadratic order. So this will be our lambda of m. And we're going to consider simulated signals, again with a stiff, a moderate, or a soft equation of state. In fact, the same choices that I showed before, and that again are not very visible. And what do we get? This is the result for C naught. So the 0th order parameter in this truncated Taylor expansion. So what am I showing here? Okay, so remember that for a given equation of state, you have a given value of C naught. There's going to be a correct value of this parameter C naught, and that is given by the dashed lines. So this is the value of C naught for the hardest equation of state, for the moderate, and for the soft equation of state. All right? And what is the other mess that you see? Well, first of all, on the x-axis, I show the number of detections made. And then you see dots. Those are the medians of my posterior density function after n detections have been made. So after n detections, if n is sufficiently large, then you can assume that your posterior density will be reasonably peaked. And so but in any case, I can compute a median, and the dots are the medians at a given number of detections made. And then I can consider the so-called 95% confidence interval. So I take an interval that contains 95% of the area under the curve. Okay? Well, this is the result. So one detection would be way down here. Now, you see that with one detection, first of all, you have large biases, and also the 95% confidence intervals are huge. There is nothing you can do. Forget about it. So you have to wait until more detections have been made, and then you see that eventually, actually relatively quickly, after, 10 detections or so, the medians actually correspond to the true values of my underlying parameter, and also the three equations of state start separating from each other in terms of confidence intervals. And then as you've made, 40 or 60, I'm going to say, detections, you're already more or less on the spot. And of course, things get better as more detections get added. Yes?
So in the moderate, the green is the moderate.
Yeah.
So initially, there's a very large bias,
Mm-hmm.
and then afterwards, it goes to the correct value, and then suddenly there's a dip.
Yeah, this can happen. So what happened there was that all of a sudden you had a really terrible measurement for whatever reason. Maybe it is a source that was particularly far away, so its SNR was barely above threshold. What can happen then is that all of a sudden you get a contribution like this, totally wrong, okay? And this will temporarily throw off the median. But then, as more detections are made, this tends to get corrected. But yes. Yeah.
Was the median taken from this law?
Sorry?
So, how do you compute this 95% confidence level?
Well, just you imagine a bar that you draw, and you lower the bar such that you reach a point where between here and here there is 95% of the area under the curve. But maybe that's not what you were asking.
Yeah. So what I wanted to ask you is that before doing this, you do not do any cutoff on the parameter space if there is one outlier or something like that?
No, we do not cheat. So if there is an outlier like this, you mean? Or no, we always take them into account. Yeah. Yeah, and that is in fact what you see, right? So as somebody observed here, for instance, the median temporarily, or even more dramatically here, for instance, the median temporarily went wrong. This is also to be expected.
But you put a cut of yes now with your school fees.
Sorry?
You put a cut of yes now above the detection threshold to your school fees.
Yeah, so I think here the SNR cut was that the SNR had to be, the combined SNR from 3 detectors had to be 8. Usually, in reality, it'll be above 8, but okay, so to be definite, yes. Yeah.
I was just worried that if you have too many observations, and one bad observation can put significant bias in it.
But only in the beginning, right? Only when the number of detections is not yet that large. If once you have, I don't know, what is this number here? Let's say once you have 160 detections, nothing is going to throw you off anymore.
Okay, so this is a posterior distribution also. So you might have some control of prior distribution of C0, right?
Yeah, good point.
How do you choose that?
Yes, excellent. So, yeah. So then I have to go way back. So I showed these plots here, right? And actually the OSs that I chose are here, MS1, here's H4, and here's SQM3. And the priors on the coefficients C0, C1, C2 were chosen flat, but in such a way that actually all of the EOSs in all 3 plots could be accommodated. Other questions?
In that plot, you marginalize over
Oops.
all the other parameters, all the other C's and all the M's and S's.
That's right. Yeah.
And
Yeah, go ahead.
Williams.
Yeah, actually, just to complete, so here I'm showing posterior densities for C0. I could also have shown them for C1 and C2, but I should have actually, but you would have seen that basically the measurement returns the prior, meaning the error bars span this entire interval, and okay, they narrow a little, but that means C1 and C2 are totally unmeasurable. Sorry?
You said that the priors were flat.
Priors are flat for all 3 coefficients, yes. Yeah.
And the other thing, could you, I mean, of course, neutron stars are not point particles. And
Right.
Of course, the model that they are not point particles is a better model.
Yeah.
But can you think that if I compare a point particle waveform model with a neutron star equation of state waveform model, I'll get a better odds ratio for the neutron star model?
Oh yeah,
I feel
definitely. Yes, yeah.
It's
So
not going to be penalized, you're saying.
well, so okay, for as far as odds ratios are concerned, like I said, things can go wrong occasionally. Like let's say even for the hardest EOS with the largest radii, right? For the point particle model, it can happen that the log odds ratio is positive, which is wrong. This is something that can occur. However, what we see in the parameter estimation is that, oh, and I should add that the results I showed for the odds ratio was for 30 sources, 30 detections, right? If I would compare that with here, with 30 detections, well, yes, it can be hard sometimes to distinguish between EOSs.
What is the quality of the data? For example, like, do you need to put high SNRs to say that?
No. So here the combined SNR from 3 detectors, 2 LIGOs and 1 Virgo, was the SNR cutoff was taken to be 8. And incidentally, most sources will have had SNR fairly close to 8 because we try to do everything legit, meaning we spatially distributed our sources uniformly in co-moving volume. And so, well, then you because of the volume effect, you do expect most sources to be far away rather than close by.
So this distribution would in principle depend on the neglection of the other orders.
Yes,
Where
it could.
you
Yeah, yeah. Yeah, well, you can already tell from this beautiful result that in retrospect it didn't matter, because what we injected, so the signals put in the data, they didn't have the simple quadratic expression for lambda of m. They had the whole expression, right, the exact one. So you can tell from this result that the quadratic approximation was good enough. Yeah. Ajith, ma'am.
A bit more general question. Here or in any other measurement where we are combining posteriors from many events,
Yes.
the spread sort of initially falls off as probably 1 over square root of n,
Yeah.
but then tends to saturate to a constant.
That's right.
value.
Yeah.
So is it possible to have a guess as to what value this will saturate to in the asymptotic limit from
I can't think, I have to be honest, I can't think of a good answer right now. I'll get back to you on that.
What was the highest SNR?
The highest SNR, well, since I think we didn't place sources any closer than 100 megaparsecs, 30 or something like that, probably.
So
Not much
can't
more
see
than
it
that.
by eye here, which one it was.
Sorry?
You can't see by eye here which one it was.
Which one it was?
Yes, so which of it?
Which the SNR? What the SNRs were?
No, but I was wondering if you would actually pick out by eye the highest SNR event here.
Ah, oh, well, no, not really. Well, maybe here, because here all of a sudden the median jumps back to the right value. So yes, here something interesting would have happened. Maybe probably a high SNR event, or a particularly nice realization of the data. That could also be the case.
How much time might it take to get 80 detections or 100?
Ah, that depends on the detection rate, which Cole discussed this morning. Yeah, we don't know. So, well, so the realistic rate that people like to quote is maybe a few tens per year. So then, well, suppose it is 40 per year, which has been quoted in an actual LIGO-Virgo collaboration paper as being realistic, God help us. But then if it is 40 per year, then, you know, after 2 years you would be here. Okay, so, right. Now, I should say that this plot here comes with several caveats that have been worked out. I didn't want to show you an ugly plot because then you would have been confused. But one caveat is that this is in Gaussian stationary noise. That is probably fine because the effect that we're looking for occurs at very high frequency, where the glitchiness of the instrument will be much less than at low. So if we had done these simulations in real noise, then probably that would not have made that would not have been a big deal. However, there are a couple of other things. So what we assumed here, both for the simulated signals and the recovery templates, was that the point particle part of the waveform was simply Taylor F2. That is the usual stationary phase approximation template taken up to 3.5 pn order in phase. Now, the effect we're looking for occurs again at very high frequency. But we know that at high frequencies, the different Taylor approximants that there are start disagreeing violently. Okay, so and for instance, had we taken one particular Taylor approximant for the simulated signals and a completely different one to search for it or to interpret the signals, then this plot would have looked very, very much different. So what you should take this plot to be is as indicative of what we will be able to do once we have the correct waveforms, quote unquote. And these are waveforms that theorists have to give us, right? So in particular in the hypothesis testing, hopefully the theorists will eventually give us in-spiral merger ring-down waveforms that, you know, apply to a particular equation of state and are picture perfect, as in, you know, we can trust them. If that is the equation of state, then this is what nature will give us. That is one caveat.
So, is there has somebody done a calculation of the same kind of plot with the EOB tidal effects included?
Not that I know.
Okay, but
No.
that is supposed to take care of a lot of these in between things to some extent and so on? Or
Yes, probably, but nobody has done it. Yes. But also, you know, in the end, you want, so that could already solve or mitigate the problem a great deal, but in the end, you also want the merger and ring down in any case, right? I'll go on to talk about that a little more. Sorry? It's been done, you say, or? Yeah, but you know, for which equation of state, how many cycles in the numerical waveform? Because that's what you're probably referring to.
No, I'm referring to the title will be on, so it's go on quickly.
Right. But I was also anticipating on myself in saying that we will also want to get information from the merger, right? And then, well, okay, I know there is an in-spiral merger ring down EOB model that includes tidal effects, but it, for instance, doesn't include precessing spins, right? So we're not there yet, definitely. But I mean, I'm extremely happy with progress that is being made, definitely. So that is one thing. We don't have the picture-perfect waveform model yet to do this. So if tomorrow there were detections already, we would be caught with our pants down. But an other and more subtle thing is that this sort of measurement is very prior dependent. And I wish I had more time because I would show you the actual results. It's a pity because I had time and I didn't include the slides. But this sort of measurement is particularly prior dependent. For instance, it depends on what kind of mass prior you choose. So in this calculation here, the masses for the simulated signals were drawn uniformly between 1 and 2 solar masses. Similarly, the masses for the templates used for the data analysis had masses were allowed to vary between 1 and 2 solar masses. Now, there is some evidence that in reality, the masses of neutron stars in binaries are fairly peaked around some value. However, we don't know of enough binaries yet to make very definitive statements as to what precisely the underlying mass distribution might be. So the honest thing to do would then be to say, well, in our recovery process, in our analysis process, we keep using a flat prior between, say, 1 and 2 solar masses. Or maybe you can narrow it down a little bit, but we want to be as careful as possible. In particular, we want to be conservative. And what you see in the case where the signals have masses that are pretty much bunched together around a particular value, whereas the prior is flat in a wide interval, what you will see is biases for each of those results. And if you're interested, I can actually show you plots later on. So that's a whole bunch of caveats, but my main aim here was to show that, yes, model selection can be made to work, and also parameter estimation can be made to work to do inference on a functional dependence. And an example in this case, the functional dependence was the function lambda of n. Right? And then so to finish, like I said, we will eventually want to add information from what happens near the merger. So for instance, for the soft equation of state, you expect a prompt collapse to a black hole. So what happens near merger is, well, it's going to be fairly uninteresting from an observational point of view because immediately you'll get a ring down, however, at such a high frequency that you can't see it. But you may be able to distinguish between that and what you get for a hard equation of state, where the 2 neutron stars don't immediately collapse to a black hole, but instead form this bar-shaped object, which spins very rapidly, and then has to shed that spin, and it meanwhile keeps emitting gravitational waves for a while longer. And if you add that information to the in-spiral part of the waveform, then maybe a lot more information can be gleaned. And by the way, despite the fact that these contributions will not add much to the SNR, we know from experience that SNR is not the whole story in either parameter estimation or model selection. So it's reasonable to expect that there will be real value in adding this sort of information to the template waveforms that we then can use to do data analysis. Okay, so this is what I had. Are there any more questions? Yes?
So how bad would be neutron star black hole binaries, I guess it will be worse than the double neutron star thing because only neutron
Sorry,
star.
what was the part, the first part of your sentence?
The same plot.
The same plot?
Has it been done for a neutron
No.
star black hole binary? Or
No.
Because it's not interesting.
I would expect it not being interesting, yeah, because of the tidal effects not being so much, and then, well, yeah.
And how does this plot and how good is the constraint with ET, the same double neutron star thing? With ET detection, you said doing many sources. How?
Yeah, that's right. So, well, that ties into Archesman's question. So, we know that the end result doesn't really go like 1 upon square root of number of sources. However, if you would do that, let's say you expect, well, 1,000 times more sources because 1,000 times.
Be better, right?
Yeah, yeah, exactly. So 2 things will happen actually. So the same sources, suppose ET is switched on, then the same sources that would have been picked up with the second generation detectors will be seen by ET with 10 times the SNR. And second effect, in addition to that, ET can see many more sources that of course are weaker because further away. Yeah.
But
and
you're
then
saying that SNR won't play that bigger role. Is that, was that the intuition that even if the SNR increases by a factor of few, you may not gain that much into the estimation of
no, I would expect that, okay, so roughly speaking, then the square root of the number of sources, that would be the dominant effect. So, and which is, you know, that's in any case my intuition, but we've already seen here on the previous slide that there's enormous value in combining information from multiple sources.
And also if the neutrons has got a small spin, how does it, I mean, how bad will the thing, you know, if you include
then the error bars will approximately become twice as large. Yeah. In fact, if people want, I can actually show the real plots because we have time, right? So why don't I do that? Okay, so what is the fastest way to get there? This is the fastest. Oh, no. Okay, so first of all, let me show you, so what should I show? Let me show first the effect of spins. So these are plots that compare the following cases. So in both cases, you pretend you know what the underlying mass distribution is so that you can use it as a prior in your analysis. Except that here, spins have been switched on. And I forget how large the spins were. It is in the caption of some other figure. I think it was Gaussian distributed with a standard deviation of 0.02. Yeah. Oh. Yeah, 0.02, yeah. So yeah, so this is then purely separating out the effect of spins. And you see that actually I think the error bars get larger by rather more than a factor of 2. But then there is also the interesting effect of the mass prior. So remember I said that, well, in reality we won't have the underlying mass distribution, and so if we recover with this flat prior, then in the case of zero spins, I'll show, to neatly separate out the effects, look what happens. You get significant biases here and here. And
so the spins aligned for aligned ones or non-aligned ones?
sorry?
I mean,
The
you have
spins?
binary pairs, right?
Yeah. So
that will depend on whether these two are aligned with our orbital.
Yeah, exactly. So well, in the so this doesn't have spins, this plot, but in the plot that did have spins, for simplicity, we assumed that the spins would be aligned or anti-aligned, because.
So it's not for non-aligned one. You are saying if we have a spins means non-aligned one.
No, they're always aligned. In these results, they are always aligned, and this is for this. Okay, this was to get an idea of what the effect of spins would be. In reality, we don't. Hang on. In reality, we don't expect them to be aligned, but we wanted to have decent statistics. That is, we wanted to be able to make a good statistical statement, and that required many simulations, each of which took several days.
That's
right?
I'm saying for to account for spins, we have different approximations, like we have
Yeah.
different orders of spin, that doesn't...
Oh, no, that we took into account. So we took spin, we included spins up to whatever order,
Even then,
2.5, yeah, whatever, 2.5 I think. But what was not included was precessing spins, that is misaligned spins, that we didn't have. But there's no expectation that, what was it, this result here would somehow get better if you have precessing spins, right?
So is SNR, I mean, it must be, but are there any other alternatives to using the term SNR and that particular value to judge how good our signal is? It's not, this is not...
Yeah, I know, but that's a valid question. Yes, there is, in fact. You could work with, so I explained earlier that you can, instead of comparing two different waveform models, what you can do also is to compare the hypothesis that there actually is only noise in the detector, and then on the other hand, the hypothesis that there is a signal from some Taylor approximate, for instance. And then, roughly, crudely, a log odds ratio of signal versus noise, I'm going to say, of 32 is going to correspond to an optimal SNR of 8. And that's going to be another exercise. Yeah.
I'd like to pursue the issue about the bias.
Yes.
And my apologies, I haven't read your paper to look at the details, but you have information about the masses from the previous part of the inspiral.
Yeah.
So you have the chirp mass to essentially perfect precision.
Yeah.
You also have some information about the mass ratio, although
Certainly.
it's less precise.
Yes.
And if they're comparable mass, then you have a certain spread.
Yes.
I assume you're taking all that into consideration when you do
Yeah,
this.
that's implicit, in fact.
So, could you explain a little bit more why you're biased?
Yeah. So the reason is that. So let me draw the distributions of the masses for the signals and then the prior. So for each component mass, let me say that this is one solar mass and two solar masses. Then the prior was simply, the prior used in the analysis was simply this interval. And then for the simulated sources, we picked a Gaussian, peaked at 1.35 solar masses, and with a spread that I forget, but I think, I'm sure it was 0.05 standard deviation.
Right.
So now, your signals come in, and the analysis code or the nested sampling code has to pick masses. Now, since it can pick, it's being asked to pick uniformly from this interval, a lot of the time it'll pick a mass that's too high. And then if you look at the way mass and the tidal deformabilities enter into the waveform, picking masses that are too high corresponds to or can be compensated by a lambda that is too low. And this is what we see. So you usually see that, for instance here without spins, that the lambdas are being underestimated.
But for a given system, so since you absolutely know the chirp mass,
yeah.
This means that for a given actual system, the masses are very strongly related. So mass 1, mass 2 has a precise curve.
Yes.
So this means that picking one of the masses too high means picking the other mass too low.
Mm-hmm. Mm-hmm.
And I'll bet that if your lower limit were 1.25, which is the lowest that we've ever seen,
okay.
Instead of 1, I'll bet your bias would be radically reduced.
Well, yes, because then more of the time it will be picking from something that is in the support of this distribution, or in the 2 sigma of this distribution.
But I mean, I suspect it's even more than that.
Okay.
Because if you have something that has a mass of 1 solar mass, then the tidal deformability, so basically the fatness of the neutron star, is much larger than it is if it's a higher mass.
Yeah.
So I'll bet that's a big component of things. So
Okay.
for example, I would also bet that if you go down to something like 0.8,
Yeah.
you'd have a considerably larger bias than
Uh-huh.
you do for
Yeah. Okay, something to be tried. Now, remind me again, did you say 1.25?
Yes.
Yeah, so is that the lowest mass observed in binaries, or is there a theoretical argument for it?
It's the lowest mass observed, and some people make a theoretical argument for it.
Okay.
But it's not a universally accepted theoretical argument.
Right. Okay. Now, well, to be tried then, but you know, you could also do other things and say, well, you know, people have actually tried to estimate using those 10 known binaries what the mass distribution of the binaries would be. So you could say, well, I'm not going to go so far as making the prior this Gaussian, but maybe I should limit it to, you know, the 95% interval and make this my prior range. I bet the results would then also very much improve.
In fact, you've actually shown it.
Yeah,
because
exactly.
you
So
made
I
that
actually,
assumption.
yeah, no, but you know, I made a stronger one, namely that the prior was exactly equal to the underlying mass distribution. But even if, something we did not do, but even if you would pick a prior that is still uniform, but on this tighter interval, I bet that the bias would largely go away.
I'm sure it would, but I think it's the lower mass limit that's the main effect here.
Uh-huh.
So for example, if your limit were between 1.25 and 3,
Mm-hmm.
I'll bet that would have a much lower bias than you would have from 1 to 2.
Okay, thanks for the suggestion. That is to be tried.
So, the question is, this 1.25, there's some theoretical argument. Is it just by running over different equations of state?
No, because you can have neutrons. So if you're sufficiently advanced species, you could construct a neutron star of 0.1 solar masses. So it's really the question of how they form. And so the 1.25, it has been argued, is from a particular type of core collapse, the electron capture core collapse. And it's been argued that there's a very tight range of baryon masses which can do this, and that these are going to give you the 1.25. So that's the argument. But you know, there are other ways people have suggested you might be able to form neutron stars. So it's a super absolute limit.
Okay, cool. Anyone else? Yes?
Chris, so with ET, do you think that the higher coefficients C1 and C2, they can be improved probably, right?
I honestly don't know. We didn't include it in this paper. I wonder if I can easily find for you the... I think I can find it fairly easily, by the way. There was a version, an earlier draft of our paper where we actually included those plots. So, I don't know, maybe this one. No. No, you know what, I'll show you those plots later. But I can simply sketch for you what they look like. Namely, for instance, for C2, but it's, already for C1 actually, so suppose this is the correct value of C1 for a particular equation of state, and suppose that the prior range was from here to there, then what you see is medians all over the place, even for a high number of detections, let's say 200, medians all over the place, and also the 95% confidence intervals all over the place, except that you do see a sort of, I don't know, tapering towards high number of sources. And then maybe as you would take this to 2000, which is not realistic, maybe you would get something. So I don't have a good feel of what this would look like for ET.
We may not be able to constrain the C1, C2.
I don't know the answer
Yeah,
because it's yet to be tried. Yeah.
And the reason why the neutron star black hole thing is not so interesting is it also that once you have enough double neutron star thing, assuming that all the neutron stars are the same equation of state, you would have already determined it pretty well. So you don't need the neutron star black hole one.
Yeah, that is one thing. There is also the danger of pollution in the following sense. So, as you know, it's not easy to distinguish between NSBH and BBH, okay, right? Yeah. And BBH has the point particle model. Right. So we wanted to stay clear of
and
that.
And also, this thing will happen at a lower frequency where the glitchiness may be more also, because neutron star black hole will bring it.
That's another point.
As opposed to high frequency.
Yes.
But still, I wonder why nobody has carried out a study with the EOB with tidal effects on the same thing, because it would have...
But are you referring to the Damour? Yeah.
I mean,
It wouldn't be difficult to code up, but here is a difficulty though. Haha. So if you want good statistics, then you'll want, I don't know, 50 sources, I'm going to say. Now, the problem is recovery with EOB is enormously slow. It takes in the order of 10 minutes to generate on a computer a single EOB waveform, and in the nested sampling process, you need approximately in the order of 1 million waveforms need to be generated. So you could, the bottom line is you could use it for injection. That is cheap, but for recovery, that would be forbiddingly
but
expensive.
there have been some, from the Japanese group, they have also proposed some phenomenological parameterization of the double neutron star thing in some. So one can, if at least some of them.
That is just EOB.
Is it EOB? Is it okay?
That is EOB also?
Yes, so there is much happiness by the fact that people think it's something good.
Uh-huh. Yeah, no, so if it is EOB based, then for now we will not be able to use it as a template. Sorry? Yeah, I was about to say there is a solution for this, but it's going to take a while before. I mean, right now only the point particle, a line spin EOBNR model has a ROM incarnation, right? So it's going to take a while. But of course, that is the direction we need to go. Yeah, absolutely. Anything else? Okay, that's it then.
I wonder if I could ask you a little bit more about this.
Sure.